So let's talk about how to do some things with probability. I'm going to run this in case I need this later. Actually, I'm going to clear this out first. I'm going to run it. And let's do some discrete probability distribution. Define the mean and standard deviation for discrete. You do need to have packages weighted.discrete.stat and the ARM package for these. You can either, if you use an RMB file, they'll be there. If not, then you just have to click the box next to them. Typing in a probability distribution, you're going to type in your variable, give it a name, and assign it to with a comma, with combining these together with commas in between. Your probability is assigned with a C. The C means again combine. You just type them in. Define the mean and standard deviation. You do mean is W dot mean of that variable and probability. Variance is W dot var with the probability, variability and probability. Standard deviation is W dot SD with the variable probability. A histogram is discrete dot histogram, variable probability, bar dot width equals 1, main equals title of graph. You can also use a CSV file and then type in the appropriate variables for the variable and probability. So suppose you have a family of have the size of the families and percent of families that have these sizes, and you want to find the mean and size of the family, the standard deviation of the family size, and then draw a distribution. So you type in your size. C is equal to 2, 3, 4, 5, 6, 7. The 7 actually isn't just 7, is 7 or more, but it's so small after that we're just going to call them all 7. Then probability is assigned to be C, and all the values for those, make sure they're in the same order. We're going to run that. That now saves those values over here. And then W.mean, size, W.var, size, probability, and so forth, and discrete size dot probability. The bar dot width just makes the bars a different size. And then instead of using title, this package uses main, and your main is equal to probability distribution for the size of the family, and xlab is the size. We'll run that. And there's our mean, variance, and standard deviation, and there's our probability histogram. If you're doing one for binomial distribution, to find the probabilities for the binomial distribution, you're going to use d.binom, r, n, comma, p, where r is how many successes you want, n is how many you pick from, and p is your probability of success. To find the probability of success is less than or equal to r, you're going to use p instead of d, binom, r, p, m, p, and then lower tail is true because we're less than, we're down in the lower part, so that part is true. And then to find the probability of success is greater than or equal to r, you're going to use that again, that p binom. Instead of doing just r, you do r minus 1 because you're looking at doing everything up here and you got to get rid of everything down there. And then n, p, and your lower tail is false because you're having everything up here. An example, if there's 20 trials, the probability of success is 0.01, and you want to find the probability of n successes. This would be probability of success equals n. This means you use the d binom because we're equal to. When you run this, and there's your probability of success. If you want to find the probability of most 3 successes, then you want probability of successes less than or equal to, which would be the p binom command. P binom 3, because my number in that parentheses is 3. 20, because 20 is how many I picked from, and 0.01, which because that's a probability of success. And I'm less than, so my lower tail is in fact true. If you want the probability of at least 16, then you want the probability of success is greater than or equal to 16, which would be again p binom, but it's going to be 16 minus 1 because you want the complement of being 16 or more is being less than 16, which is 15 or less. So that's why it's 16 minus 1, 20.01. Lower tail is false because, again, you want everything up here. You don't want the stuff down there. You're not doing the lower tail. Run this one, and there it comes. Storing the values of random variable and probability values. If you want to store all those values, you can type in success is equal to C again, 0, comma, N. This is where it will combine them together or tell you how many there are. It's always from 0 all the way up to N, whatever your N value is. You want to say the probabilities for those values, you'd have your probability value is assigned to be that D binomial 0 to N. So it calculates all of them for N and P. So as an example, we have 20 trials, and the probability of success is 0.01. If we want to save these, then that would be probability of success is C 0 to 20. Probability values are D binomial 0 to 20, 20.01. Success will display the values of the variable. Probability values will display the values of the probability values. And there they are. So there's all my success values. That's from 0 all the way up to 20. And then here's all the probability values that go with them. I should mention that R doesn't write, most computers don't write numbers that are really small and more than 4 decimal places in standard notation. Instead, it will give it to you in scientific notation. As an example, this number would be 5.32 e to the negative 9 in R. This is how most computers do it, is they put it into scientific notation. They use an e to say this is my exponent. And so you can actually write this as 5.32 times 10 to the negative 9, and not the way that R writes it, because you have the ability to write in scientific notation. If we're in a normal distribution, define the probabilities of a normal distribution that shows you the graphs for probability of values are less than some value. You use XP norm, R mean, standard deviation, lower dot tail. If you want the probability values for more than, you use XP norm, R mean, lower tail is false in this case because you're more than. If you want to find in between two values, then you would take the upper value area, subtract off the lower values area. I don't know why I said that. This is supposed to be true. They both should be true because you want to take the one value and subtract off the other value. So they both should be true. All right, so I used XP norm. You can also just use P norm and not with the X. The X will graph it for you. The P norm will just give you the value. To find the values that you know the area to the left, you use XQ norm. The area to the left, mean, standard deviation, lower dot tail is true. If you want to know the area to the right, you know the area to the right, then you use XQ norm, area to the right. And then mean, standard deviation, lower dot tail is false. This also shows the graph. So an example, if the mean is 272 and the standard deviation is 9, and you want to know the probability of being less than 250, then your XP norm will be 250, 272, and it's your standard deviation. Lower dot tail is true because you're less than. Again, you get a nice graph. So you can see the shaded that it gives you. It actually gives you the Z value it calculates. And then you click on this to find actually a probability value. So here's your probability value of that happening. If the mean 270 and standard deviation is 9 and you want P probability that's greater than, then again you use XP norm. My greater than 350, sorry about that, 305. And then my standard mean is 272. My standard deviation is 9, and my lower tail in this case is false because we're greater than. And I can run that. And again, it shows you the graph. You can't see much because there's not much up here that's being shaded. And you can get your probability value by just clicking on the other part. If you know the mean is 272 and the standard deviation is 9, and you know the probability to the left of X value is 10%, and you want to find X, then use XQ norm. 0.01 is your probability. Your mean is 272. Your standard deviation is 9, and your lower dot tail is true because we're to the left. Okay, I can run that. It'll show me a nice graph of that. It's showing me this is the area as I'm wanted. It gives me my Z value, and you click over here, it gives you that data value. The student's t-distribution, if you're using a t-distribution, you use xpt for the probability of a t. Again, R is that value you're looking for, your degrees of freedom you need to put in there. This is finding the probability that t is less than some value. Your degrees of freedom is whatever your degrees of freedom are equal to. You use xqt, p degrees of freedom equals whatever your degrees of freedom is to find and know. If you know the probability of t is less than some value, and you're trying to find that. So an example, if we know the degrees of freedom is 52 and we want to find the probability that t is more than 7.707, then we would use xpt, 707, degrees of freedom is 52. In this case, because we're more than, our lower tail is false. And again, this graphs it up and shows it to me. You don't see much because we're being more than 707, so you're not seeing where that is on your graph. But there's your probability value. If you know the degrees of freedom is 19 and you know the probability is less than 0.01, and you want to find R, then using xqt 0.01, degrees of freedom is 19, and in this case, the lower tail is true. And there's my graph. There's that area I have. And there's my t value that goes with it. It's negative because it's below the 0. If you happen to want to do the chi-square distribution to find the probability for the chi-square distribution, you're going to use xp chi-square. Put in your value. You should have your value there. And then your degrees of freedom, and then your lower delta is false. So in this case, if I know 4, my degrees of freedom is 3, I can then run this and it'll come up with that value. It's always going to be on the right tail of it because of the way the chi-squared works. If you want to create a normal quantile plot, this is a graph. So it's a graph function underscore QQ for quantile plot. You're going to have your variable, tilde your variable, and then your data equals data set, and then title it. Draw a normal quantile plot for this data set. You would run this. There's your normal quantile plot. Whatever your data set is, whatever your data is, I just happen to put a little data set in here. All my variable data, all the data set example, and there's my graph.